start. I'm a PhD student at CMU, and I'm going to be talking about our work on drawing reliable conclusions with synthetic simulations from LLMs. So recently, a lot of work in the LLM simulation literature has focused on drawing conclusions based on the simulation data. And this has been employed in a lot of applications such as early pilot studies and more exploratory studies such as hypothesis generation. But a question one may ask is, are there tasks that would benefit from aggregation? And what I mean by aggregation is a combination of the LLM simulation data with human data. And how do we make reliable conclusions when these different data sources are combined? So I'll illustrate one very specific task. So say I'm a social scientist and I'm interested in estimating the effect of hedging or markers of uncertainty on perceived politeness. And what I have access to is a corpus of conversational text. And the challenge is that human annotation costs are costly, and so I only have a small set of labeled text data. And a potential solution that a lot of practitioners have been employing is to use an LLM as a cheap labeler. And so you can use the LLM to obtain predictions for your covariates or outcomes of interest. And past works show how to do this in a principled manner. They show how to combine model-generated data in the form of predictions with real data. And it explicitly accounts for when there's this mix of But a question one may ask, a more forward-looking question, is can we leverage synthetic simulations in a principled way? So going back to the social scientist example, perhaps I want to use the LLMs not as just model predictions, but now I want to ask the LLM, can you simulate some example text for me for this task? But now the challenge is that the text does not come from the same underlying distribution. And so naively aggregating the real data and the synthetically generated simulations result in greatly biased estimates. And so our work focuses on addressing how do we generate synthetic simulations or broadly synthetic data to be even used in a principled manner. And then how do we combine them with real data for reliable downstream conclusions? So on to the first question. The key point to simulating synthetic data to be used in a valid way is that it needs to be conditioned on a real sample. And this correlation structure between the real text and the simulated synthetic text is going to prove critical for our method that I'm going to show in the following slides. But we have a very concrete example of the prompt that we use here. Basically, consider the following user request that contains hedging, generate a new example of a request that also contains hedging. So there's a lot of different prompting strategies that LLM simulations use. Many of them use conditioning on personas, but here we're interested in conditioning on specific covariates. So after this procedure, we have now real text labeled by humans, and we have this synthetic text labeled by LLMs. So now how do we combine these different sets of information? So before going into our method, I'm going to give a very high-level overview of generalized method of moments, which is the framework that our method utilizes. So the GMM is a very widely used moment-based estimation framework. And the key point is that the true parameter values, at the true parameter values, the moment conditions should equal 0. And so moment conditions are sample averages of certain functions that need to equal 0. And so I'm going to give a very a toy example. So let's take MLE for logistic regression. So we want the gradient to go to 0. If we explicitly write this out, we have what's on the right-hand side, which is that the expectation of the score function needs to go to 0. And the moment condition for logistic regression is exactly this function. So it's the score function that needs to go to 0. And so we need to define moment conditions according to whatever statistical model that we're interested in. And GMM not only just accounts for MLE, but includes like many statistical models. And so with that in mind, I'm going to give a high-level sketch of our method, our estimator. So first, what we do is we define for every real data moment, we're going to add a synthetic data moment. What I mean by this is on the left-hand side, you can see that there is a function defined in terms of the real data x and our target parameter theta. And for that moment, we're going to define the same analogous one using now the synthetic data, which is x tilde, and an additional parameter, eta. And the reason why we introduce an additional parameter is because we don't want to make strong distributional assumptions. And then what we do is we just stack them together. We stack the real data moments and the synthetic data moments, and this forms our moment vector for the GMM. And now what the GMM does with this moment vector is it learns a weighting matrix that's going to reflect the correlation between these different moments. And so what the optimal weighting is actually going to produce is a combination of these moments that reduces the variance of estimation of the target parameter. So basically, if there is correlation between the moments, it's going to improve the efficiency of estimates. And the intuition to why we might believe this works is that they should be correlated if the synthetic data was conditioned on real data, which is how the simulation data was generated. And we also have that the statistical guarantees that we want follows from standard GMM conditions. So more under the hood, trying to understand why does synthetic data help? Like why do these correlations help? Basically, what's going on is that when the synthetic moments are predictive of the real data moments, this is going to reduce the variance in estimation of the target parameter. When they're independent from each other, the variance is going to reduce to one dependent only on real data. What this means is that if you have very bad quality synthetic data, you're never going to do worse than not having used it in the first place. And so the more mathematical intuition of what is going on here is you can think about the asymptotic variance is as kind of like a leftover variance after you regress the real moments onto the span of the synthetic moments. Yeah, so now we're going to see how well this works in practice. So with the same running example of looking at the effect of hedging on perceived politeness, we see that indeed compared to only using real data, using the combination of real and synthetic data via our method results in very large reductions in MSC. So you can see like up to 50% reduction in MSC, especially in very low labeled regimes. Another thing we do in our paper is we adapt existing debiasing methods called PPI++ and re-PPI. And what these debiasing methods do is they're able to integrate model predictions, but they're not able to integrate fully synthetic simulations. And so what we do is we make some non-trivial adaptations so that they can be applied to our setting. And you can see that essentially our method is able to use the synthetic data more effectively, resulting in larger drops of MSC. And so during the talk, I was mainly going through this running example, but in our paper, we show that the same conclusions hold for a diverse set of computational social science tasks, and also a diverse set of statistical inference tasks, totaling up to 8 different tasks. We also show that our method retains valid coverage across all tasks, and also results in tighter confidence intervals, and large gains in effective sample size. And what effective sample size means here is how many human annotations the method saves while maintaining the same performance. Yeah, so high-level takeaways is that synthetic simulations really has the potential to bring large benefits in downstream inference tasks. But how you combine the data is a very crucial factor in order to bring out those benefits. And so our GMM approach kind of allows us to retain these benefits from synthetic data without compromising the guarantees that practitioners need to make reliable conclusions. And just some food for thought, like as the usage and promise of foundation models continue to grow, pipelines that incorporate their outputs are going to become more and more complex. And so it's very important to try to think about more safe and reliable aggregation strategies as we move forward. Thank you.